Okay, so time for us to get started. Technically, we had a class on Monday, but we decided that it was okay if we canceled it, so I'm gonna stick with that. We'll have a canceled class. It means we'll miss sort of a couple of slides that I had planned to do, but it's fine. We're gonna get all the basic concepts covered. The makeup midterm, I'm glad to see so many people participated. I think overall it was a pretty good exercise. And one of the things I'm hoping you kind of take away from it is to see what constitutes a complete answer. And I hope this is going to give you a real edge for the final exam. This makeup work that you passed in, like I was pretty clear that I expected it to be perfect, but that's because you had lots of time and you were allowed to have lots of help. On the final exam, I would be a little bit flexible off perfect. You know, if you write things with poor grammar, but you get the gist across, then that's fine. If you put down your equations and they're a little bit scribbly and it's hard for me to read your handwriting or follow the process on a final exam, that's kind of okay as long as I ultimately can follow it. But hopefully you kind of got the idea of the kind of details you need to include. So I hope this was a good experience for everybody. Even though I recognize probably a lot of people don't care and just want the better mark, but that's a valid thing to want to. So, last day, the lecture had to be posted on YouTube because I really couldn't afford to give up another one. So that was up there. I'm going to assume that people did have a look at it. It was about magnetic fields due to current carrying wires. And in today's class, we build on those concepts a little bit. So, what the topic of that last lecture was that when we put a current through a wire, we get a magnetic field. That was the whole idea. We know what the field looks like and we can figure out what it's equal to. Faraday came along, and he certainly was pivotal in some of this electromagnetism stuff. And he asked the flip question. He said, okay, we see that a current carrying wire makes a field, but is the opposite true? Would a magnetic field make a current? That's an interesting question, right? Does it work in reverse? So we can answer that question, and we can see how it works. So what I've got here is a galvanometer. It measures current or voltage. And the other couple of things I have, this is a stack of rare earth magnets. It's got a really strong magnetic field. And this is a solenoid. It's just a coil of wire. So this is wire, this is a magnet. This is going to measure the current that's inside the solenoid. So if I take the magnet and I poke it inside, you can see that we get a current. Right? And if I pull it out, we also get a current. If I push it in slowly, we get a little current. If I pull it out fast, we get a big current. If I put it in, and if I just rotate it, that doesn't do anything. So this is kind of like magic, okay? This is really cool. I'm taking a magnet and I'm waving it around and I'm getting current. This is like the definition of clean energy, right? I'm producing nothing that hurts the environment here. I'm just moving a magnet back and forth and I get all the energy I want out of it. I get the current. So this is really cool stuff, and this is what Faraday talked about. How does moving this magnet, how does that kind of change make a current? Okay, so we're going to start looking at those things. So Faraday asked the question, does a magnetic field create a current? And the answer to that question is yes, but only if B changes. If we put the magnet inside and hold it still, we don't get anything at all. So let's see if we can explain this effect. So I've got some of the words preloaded here so we don't have to write down all of the notes. So the setup is, I have a magnetic field. My magnetic field points into the page. That's what these crosses mean. I've got a conducting bar, so this is full of charges which are free to move. And I'm gonna pull that bar to the right. So it's gonna move to the right with some velocity v. So let's think about what happens to the charges in the conductor because they're moving in a magnetic field. So the charges are gonna feel a magnetic force. That force has a magnitude of FB equals Q times V times B times the sine of 90 degrees. Velocity is to the right, magnetic field is into the page, so the force is QVB. What about the, thank you. What about the direction of the force? So there's our magnitude. If we want to get the direction, let's think about what's happening to a positive charge. You can just stay seated. You don't have to kind of stop in the middle of class and bring it up. Yeah. It's a little hard to keep a train of thought.
Sorry.
Let's think about the direction of the force on these charges. So a positive charge is moving to the right. There's a magnetic field into the page. It feels a magnetic force that points up. So a positive charge in the conductor will feel a force that points up. So if the charge is positive, force is up. The negative charge, so conductors have positive charges and negative charges. If we have a negative charge, we do our right-hand rule. The velocity is this way, the field is this way, the force is this way. That would be the force on a positive charge. This is a negative charge, so we have to rotate the force by 180 degrees. If the charge is negative, force is down. So the negative charge will feel a magnetic force that points down. So what happens if positive charges have an upward force is that the positive charges will move up. So those charges move up to the top. If the negative charges have a force that point down, they're going to move down. Okay? So the positive charges have an upward force, they move up. Negative charges have a downward force, they move down. So the result of the magnetic force is that positives move up and negatives move down. If the positives are at the top, the negatives are at the bottom, the charges separate. And let's ask what happens if we have positive charge here and negative charge here. You get an electric field. Okay, so there's going to be an electric field established inside that conductor just because we move it. The electric field will point from the positive to the negative. So this results in an induced, and we say induced because this field is created by the motion that we make. In an induced electric field, if we have an electric field over this distance L, we're also going to get an electric potential. So we also get an induced potential difference. Okay, so that's pretty interesting. You move a conductor through a magnetic field, and all of a sudden, we get electric fields and electric potentials. The induced potential difference typically is called epsilon. That's the symbol we use for potential. That's going to be the size of the field times the separation. And this only happens when the bar moves. If the bar is still, this does not happen because we only get the force when the charge moves in the magnetic field. Okay, any questions here? No, you can just sit down. Any questions about this stuff? So let's see if we can think about the size of this potential in relation to what's happening here. So let's think about what's happening. We're dragging this conductor to the right, And we can say that the charges are going to reach a steady state. So they'll get where they're going and they'll stay still. They'll reach an equilibrium at some point. And they're going to reach the equilibrium when the net force on every charge is 0. So they're going to keep moving. It's going to feel a force. Charge is going to build up at both ends. The electric field is going to get bigger and bigger. At some point, the electric force will balance with the magnetic force, and they'll reach an equilibrium state, and the net force will be 0, and the charges will stop moving. So it'll reach a steady state when the net force equals 0, which means that the magnetic force on every charge, take away the electric force on every charge, equals 0. Okay, so what happens over time is that our positive charges drift to the top. Our negative charges drift to the bottom. Every charge is going to feel a magnetic force that points up. That comes from our right-hand rule. They also feel an electric force, because that's charge times electric field. They'll keep moving. The charge will keep building up until at some point these forces become equal, and these charges will no longer drift up because the electric force is strong enough to keep it from drifting up. So that's what's going to happen over time. Our magnetic force, we said that had a magnitude of Q times V times V. Our electric force has a magnitude of Q times E. So we can rearrange this equation, divide both sides by Q. We see that V times B equals the size of the electric field E. So here's a relationship between the speed at which it's moving, the field it's sitting in, and the induced electric field that's going to be created because we're moving it with this speed. If we remember that E is the potential over the distance, then what we get is that induced potential is equal to the field times the distance equals E times L times E. So the induced potential depends on the size of the field, the length of the conductor, and how fast we're moving it through there. Okay, any questions here? So this is what happens when we pull a bar through the field. What happens if we take the bar and we make it part of an electric circuit? So we're going to take our conducting bar, that's the blue bar we have here. This is the same bar that we had in the last problem. We're going to put it on a set of conducting rails. Those rails have a resistance R. And we're going to put the whole thing in a magnetic field that points into the page. So this is our setup. So now we've got a complete circuit. So we have conductors in contact right here. So this is a full complete circuit. If we have a full circuit, we know that current's going to be allowed to flow. So let's do our setup again. Let's take our bar and let's pull it to the right. So I'm going to say I'm going to pull it to the right with some pulling force. Fast pull. You can just sit down. I'm going to pull it to the right. It's going to have some velocity, okay, because we're moving it to the right. In our bar, the positive charges are going to experience a magnetic force. So V cross B gives us the magnetic force that points up. So each of those charges feels a little force that points up. So the charge is going to start to move up. The charge is going to flow around the circuit since we now have a connected circuit. Charge flowing around a connected circuit, this is current. So this current we can label with M. So what's happened is that we've pulled this bar to the right, the charges feel a magnetic force, the charges start to flow, flowing charge is current. So by pulling this bar, we've induced a current in this loop. So we get a counterclockwise current induced in the loop. We know that the potential across the bar is going to be B times L times V. This is what we found on the last page. So let's layer in Ohm's law here. So Ohm's law is V equals I times R. For potential, we use epsilon. Epsilon equals I times R. So B times L times V equals IR. So I is equal to BLV divided by R. Okay, this is pretty interesting. So we just move, by whatever means, a conductor in a magnetic field. So that means we induce a potential. When we induce the potential, we induce a current. And the size of that current depends on the field, the size of the conductor, how fast we pull it, and the resistance of the whole thing. So now we're getting current flow, which is what we observed when I moved the magnet through the loop there. So same thing is happening, same idea. So this is the current induced by moving the bar. Good to hear. Okay, so now let's think about the forces. So we have, if we think about what's going on now, we have current flowing through this sliding bar. That makes this a current carrying wire. This is a current carrying wire in a magnetic field. It's going to feel a magnetic force. Okay, so all of this stuff might be starting to feel a little circular, and it is a bit circular, which is kind of interesting too. So this current carrying wire is in a magnetic field. So I is in the magnetic field B. So it feels a magnetic force, which is equal to I times L crossed with the magnetic field. So this is the magnetic force which is induced on that moving bar. So as we pull it, the current flows. Because the current is in a magnetic field, this starts to feel a magnetic force. This is the induced current, so this is the induced current in the bar. This is the length of the bar, and this is the external field. So let's get a sense of the direction of that force. So we look at our slider, the positive charges are moving up, that means the current is moving up, that's our thumb. The external magnetic field is into the page, that's our index finger. Our extended middle finger is the magnetic force that points to the left. So the induced magnetic force on the slider is to the left. So what's really interesting, I think, about this is that we pull it to the right. The result of pulling it to the right is that there's a force to the left. The induced magnetic force will slow things down. So this opposes the motion. Slows the bar. Anybody hear of magnetic braking before? This is magnetic braking. This is how that works. So brakes on most cars, certainly on my cars and on my bicycle, it's physical, right? You press the brakes, something grabs, it pushes against the rotors, and it starts to wear down over time. With magnetic braking, that's not how that works at all. And I've got an example of that here too. So what I've got is just two aluminum bars. They're hanging on a pivot, and if I let them go, pull them up the same height, they swing exactly the same. These are the same metal bars. So they're going to swing with exactly the same period. If you remembered a physical pendulum, you could calculate the period and all that sort of thing. The other thing I have is a pretty big magnet. It's really strong. It's been around for a long time. So now what I'm going to do is I'm going to move this magnet so that one of my bars is between the poles of the magnet. It's not touching, okay, so there's no friction here. It's not going to touch at all. And I'm going to do my experiment again. I'm going to hold this up, and I'm going to let it go. Okay, that one stops immediately, right? Without any friction, without any resistance. So there's no wear and tear on this at all. This is why magnetic braking is a good thing. So you can slow things down without ever touching them or destroying them. So as the bar moves through the magnetic field, the charges start to move, it makes what we call eddy currents. They go in little circles inside the bar. Those currents in the bar feel a magnetic force. The magnetic force opposes the motion and it makes the bar stop. So that's how magnetic braking works, and I think that's kind of cool. I think I meant to do that demo later, but it kind of belongs here too. So that's what's happening with the forces. So this is how magnetic braking works. And then let's take it one step further. Let's think about the next thing that we know. This bar is carrying current. We can think of this as a current carrying wire. What happens around current carrying wires? They make magnetic fields. So this current carrying wire makes a magnetic field, which is big circles around the wire. The direction of the field right here, we would use our right-hand rule. So we've got our big circles, our current goes up. The direction of the magnetic field on this side points out of the page. So we get an induced magnetic field, which points out of the page. So what is the result of the current in the bar? It induces a new magnetic field.
So two opposing magnetic fields? Jesus, mumbled through that. Is there one field going in and one field going out?
Yes, the induced field points out, that's the green circles. The existing field points into the page. So these are in the opposite direction. And if we come to the place where I'm going to finish, we'll sort of discuss the same direction, opposite direction. So I hope we'll get to that. This induced field, we could calculate with our equation, mu naught times the current induced divided by 2 times pi times r. Okay, so you could figure that out if you wanted to. And the direction of this one is out of the page. Okay, questions to here? Okay, so there's a lot of physics going on in these little loops. Okay, a lot of interesting stuff. So now the next bit, because we would like to establish a way to think about how is all this stuff induced and how do we figure out what all these things are. So we just went through it sort of qualitatively. There is a quantitative way to do it, and that's what we're going to get going on now. So what we just looked at, what we saw was that magnetic field was in an area, and we made some changes and we induced some fields. Okay, so we had magnetic field lines and we had an area. We're going to define a new concept called magnetic flux. And magnetic flux is a quantity representing the number of magnetic field lines cutting through a surface. It is more or less exactly like electric flux. Electric flux tells us about the number of electric field lines cutting through an area. Magnetic flux is the number of magnetic field lines cutting through an area. Okay, so same idea. The magnetic flux is the scalar product between the magnetic field and the area vector. So it's the size of the field times the size of the area times the cosine of the angle between them. The units are Webers, where a Weber is a Tesla times a meter squared. Different places will either use Webers or Teslas times meters squared. They're both valid, whichever you prefer is fine. So just as a refresher of flux, we will do one example of how to calculate a flux. We'll only do a simple example because a simple is good enough for our purposes here. So I've got a 3D image of an area which is tilted to the surface at an angle of 30 degrees. I've got a magnetic field coming through horizontally. I know what the flux is. I know what the area is. I'd like to find the size of the magnetic field. So first of all, I'm gonna take that 3D view and I'm gonna draw a side view. In my side view, so I'm looking from over here on this side. So I'm looking at the edge, here's my 30 degrees. My magnetic field is horizontal, so my magnetic field comes out like this. There's the direction of the area vector. We did lots of this with electric fields. We said an area vector was perpendicular to the surface. That's still true here in this problem. So our area vector is perpendicular to the surface. We can write down our equation for magnetic flux. Magnetic flux is B dot A, which is B times A times cosine theta. Theta is the angle between B and A. So this angle is theta. We have a little bit of geometry to do to figure out theta. Not much geometry. So this B is horizontal, this dashed line is horizontal. When we have horizontal lines, it makes like a Z and the interior angles have to be the same. People kind of remember that from high school. A is perpendicular to the surface. So right here we have a right angle. So 90 degrees equals theta plus 30 degrees. Theta is equal to 60 degrees. So we're trying to find the size of the magnetic field. That's going to be flux divided by the area times cosine theta. The magnetic flux, 0.90. There's not much difficult you could ask in a question like this. So a little twist is let's make them in milliwebers instead of webers. So you just got to catch that the M stands for milli, and that means times 10 to the minus 3. And then the other twist is that the area is given in centimeters squared. You'd have to convert that to meters squared to get to our SI units. So 3 centimeters squared is 3 times 10 to the minus 4 meters squared. Multiply that by cosine of 60 degrees. And the size of our magnetic field is 6 Teslas. Okay. So there's not much difficult we can do with magnetic flux here. Okay, are we good to here? So magnetic flux is like electric flux, except it's magnetic field lines through the surface. Okay, let's pull it together. So, what we have seen in class and can be observed in experiments is that we get an induced current and an induced potential. Sometimes that's called a motional EMF. And we see that when, not just if our magnetic field changes, but if our magnetic flux changes. So if the field changes, we definitely saw a current, but also if the area changes or if the relative angle changes, we would also get currents in those cases. So how do we relate the induced potential to that change in magnetic flux? Well, for systems in general, the induced potential, and this is Faraday's law, is equal to the negative of the change in magnetic flux divided by the change in time. So this is Faraday's law. So epsilon is the induced potential. Delta phi is the change in magnetic flux, where magnetic flux is B dot A. And delta T is how long it takes to change. So we saw a difference if I push the magnet in slowly versus quickly, so the amount of time definitely matters. The negative here is really important. The negative says that the induced potential, so the potential we get created, which end is high potential and which end is low potential, it's always going to be induced so that it opposes the change in magnetic flux. So when we looked at our bar slider problem, we pulled the slider to the right, everything got induced so that a magnetic force was to the left. That's what this says. Okay, so when we make a change, all of the things will be induced so as to oppose that change. So we're always trying to minimize the change. Okay. Questions here? All right, conceptual question. So, have people observed, I definitely have, if you plug in or unplug one of your appliances, like an iron or a computer, my toaster oven up in my office, have you ever seen it spark? Definitely a few nods. That happens, it's a real thing, it could be predictable, and it can be explained by Faraday's law. So let's say we're going to unplug something. When it's plugged in, there's a current flowing, right? So it's plugged in, there's current coming out of the wall, goes into your device. There is definitely a current flow. When we unplug it, we are all of a sudden turning off the current, which means we're turning off the magnetic field. So originally there's a current flowing through. Because there's a current, there's a magnetic field around it. When we unplug it, we've turned off the current, we've turned off the magnetic field. Faraday's law tells us that this will induce a potential to oppose that change. So as soon as we unplug it, it's going to induce a potential between the prongs of your plug and the inlet of the outlet, right? So in that little space between your cord and the wall outlet, it's going to induce a potential. Those potentials are so high that we actually get a dielectric breakdown. The potential is so high that the electric field exceeds 3 million volts per meter, and that's why there's a spark. So we unplug it, we break the current, we turn off the magnetic field. Faraday's law says that there's a new potential, a new field created to maintain that current over the air, and that's why we get the spark, because the current is actually traveling through air. So I think that's kind of interesting. So the next time you see that happen, kind of that's why it happens. So now we can talk about some of that direction stuff. Kind of takes us to Lenz's law. Lenz's law is a tool that we can use to think about what is the direction of the induced things when we change magnetic flux. Okay, so Faraday's law says that if we change flux, there is going to be an induced potential. If there's a potential, there's going to be an induced field and an induced current. Okay, so those things happen whenever we change magnetic flux. Lenz's law says that there will be an induced current if the magnetic flux is changing. The direction of the induced current is such that the induced field will oppose the change in flux. So if there's a change in field, a new field will be induced, and the new field will oppose the change in field. Okay, let's put it into practice. So in this example, I've got a bar magnet, and we looked at these right in the beginning when we started our section on magnetic fields. We know that magnetic field lines come out of the North Pole. So our magnetic field lines coming out of the bar magnet look more or less like this. Let's ask what happens if we take this magnet and we push it to the right. Okay, so let's see if we can predict what's going to happen. So I'm just going to put a velocity vector there because I'm going to push the magnet to the right. So let's walk through it step by step. If I take my magnet and push it to the right, does the magnetic field inside these coils get bigger or smaller? So I'm taking my magnet and I'm pushing it closer to the coils. It's going to get bigger, okay? So the magnetic field is really strong close to the magnet. So when I push it this way, B, which points left, increases. I don't have much space, so I'm going to write I and C instead of increases. Okay, so this is the external change that we are making. We are increasing the magnetic field that points to the left. So according to Lenz's law and Faraday's law, a new magnetic field will be induced to oppose this change. Okay, so if I've made B to the left bigger, the way to oppose this is to create a B to the right. Make sense? So like I go from 50 Teslas to 100 Teslas, all pointing left. I don't want that to go up to 100. I want it to stay at 50. The only way to get it to stay at 50 is to induce a field of 50 to the right. So I don't want it to change. So B is induced right. So the new magnetic field induced will point this way. Kind of okay with that idea? So we're opposing the change. We've made it bigger to the left. To balance it, we have to get a new field pointing to the right. We want to cancel out that increase. So what does that mean in terms of a circuit? So I've pushed the field near a coil of wire, which is what I was doing in kind of the initial demo. I pushed a field in a coil of wire. We saw in the galvanometer that in induced a current, we know current has a direction. We can find the direction of the induced current by using the right-hand rule. So I'm going to imagine my hand is gripping this loop, and I want my fingers to reflect the induced magnetic field. So my fingers are going inside the coil, inside here, and my thumb is showing the direction of the magnetic field in the front of the coil. So my fingers are inside the coil. My thumb is pointing down, so the current in the front of the coil here must be flowing down. So B is induced to the right. I induced is down in the front. Yeah.
How do you know where to grab the coil from? I need you to grab it from the left. You get it
The thing that matters, so that's a good question, I'm glad you asked, is our right-hand rule says that my thumb is current and my fingers are magnetic field. So I wanted to put my hand so that my fingers were matching the direction of the induced field. So I have to put my hand on this side, because if I put it on this side, I guess I could do it on this side. So my fingers have got to be going this way, right? So then my thumb points down, right? So whether I put my hand here or here, the field still points to the right and my thumb still comes down. Yeah, okay, that was a really good question. Okay, so let's do another example that maybe you won't find too challenging. So in this example, what's the direction of current flow in the loops here if I pull my magnet away? Okay, so if I'm gonna pull the magnet away, B, which points left, does it increase or decrease? Decreases. I pull the magnet away, I'm further away, it gets smaller. If I pull the magnet away and this magnetic field gets smaller, what induced field do I have to make, what direction, to keep it the same?
To the right.
It's got to point to the left. So I've pulled my magnet away, the field got smaller, I don't want it to get smaller, so I have to induce a new field to the right to keep it the same size. Okay, so I always want the field to stay the same. So I have to make new field to the right, be induced, to get my field to stay the same. Be induced, oh, left, sorry, oh, I have a whole left right thing. My induced field has to keep this original field just as strong, so it has to induce to the left to oppose that change. If the magnetic field is induced, this direction, so I'm putting my fingers in this direction. What is my thumb doing? My thumb is pointing upwards, so the current in the front of the loop has to go up. Make sense? Okay, let's just do a different geometry. Might be a little easier to look at, especially with the right-hand rules. So we said that it was changing the magnetic flux that induced the new field and the new current. And to change magnetic flux, you can change one of three things: the strength of the field, the size of the area, or the relative angle theta. In this picture, we're going to change the area A. Okay, so we start with a circular coil that's its full size, all extended, and then we squish it together. Okay, so this is our step. We start with the full area and we make the area smaller. So in this process, as we go from here to here, we decrease A. If we decrease the area A, what happens to the flux? Does the flux increase or decrease? Flux is going to decrease. So the magnetic flux, which is B times A times cosine theta, will decrease. So then, according to Faraday's law and Lenz's law, what we need to have induced is something that will increase the flux. So our change decreases flux. The induced change will have to increase it to oppose the decrease. Okay, so in this loop right here, we're going to get an induced field that's going to increase the magnetic flux. If we're going to increase the magnetic flux, what direction do you think the induced magnetic field has to be? If you want the flux to get bigger. Got to point into the page, okay? So the field now points into the page. The flux is pretty small. A way to get the flux bigger is to have more field into the page. If you like to think about it visually, you could look at literally the number of x's. So inside this circle, there are 6 x's. Inside this circle, there are 3 x's. To get the flux the same, we need 3 more x's. So that would be a more visual way to look at it if you prefer. So we must increase the flux. Therefore, we have to induce B in exactly the same way. So we induce B into page. If we're going to induce the magnetic field into the page, we can use our right-hand rule to sort out the current. So I'm going to point my fingers into the page. I'm putting my fingers in the middle of the loop, so it's like I'm grabbing this section right here. My thumb points down, so it says the current in this section points down because my fingers are into the page with the magnetic field, and my thumb shows what the current does right here. So my current points down. That's my induced current. It flows around in this direction. Do you feel like you're starting to get the swing of it? It's really neat stuff. I feel like we should do one more example of that. Okay, I've got another one ready to go. So in this example, we've got a current carrying wire. It's carrying current to the left. What is the direction of the current induced in our loop if we increase this current I? Okay, so this is a little bit complicated. It's okay, we can work through it step by step. So first of all, we'll recognize that this current carrying wire has a magnetic field around it. Let's get the direction of the field. We know that the field makes big circles around the wire, and our fingers will show the direction of the field. So our thumb is our current. The magnetic field up here on top of the wire, my fingers are poking into the page. So up here on the top, the magnetic field is into the page. That's not very relevant, but it's true, so let's put it in the picture. The part that's relevant is what's happening down here at the loop. Over here on this side, my thumb is to the left with the current. My curled fingers are showing the magnetic field. My fingers are poking out of the page, so the magnetic field is out of the page. So down here, my magnetic field is out of the page. So this is the magnetic field made by the current carrying wire I. Good to there? So that was kind of the topic of our last class. If we increase I, let's ask what happens. So if I increase this current, I'm going to increase the magnetic field, which points out of the page. I'm going to follow that one because I is, or B is mu naught I over 2 pi r. So this is our external change. We're increasing the current, which increases the magnetic field, and that magnetic field is pointing out of the page. If we've made this field bigger, how do we oppose that change? What kind of field do we have to induce to oppose that? Into the page or out of the page? Got to be into the page. So I've made a big field out. If I want to cancel part of it, I need part of a field in. So B induced is in. If the magnetic field induced is into the page, we can get the direction of the current. So it's like I'm grabbing the bottom of this loop with my hand. My fingers are pointing into the page. My thumb is showing the direction of my current. So the current has to come around this way. There's my induced current I. So that's got to come around clockwise. So the last couple of slides I had were applications of this. I'll show you one more demo, just because this is really kind of neat too. So this is that whole thing in action. If you've come to demos in the physics department before, you've probably seen this. We call this the jumping rings demo. So this is another one of these things that's been around the department forever, and it's pretty cool. So what it is basically is an electromagnet. I've got coils of wire here, a solid core. When I turn on the current flows through it, makes a magnetic field. What I'm going to do is put a loop on top. So I'm just going to put my loop here. It's not doing anything, and next I'm going to turn it on. Okay, so right off the bat, it's neat, right? I put it on there. When I turn on the current, the magnetic field changes. It induces a new field, induces a current. It feels a magnetic force that pops it off. Okay, and then we can do it for bigger loops. Okay, it still pops off, but not quite as impressive. And then I will do this one again. Okay, why didn't this one work? Anybody got any ideas? I heard a voice. This is kind of neat. When I do this with school kids, I always ask them if they broke it. It's not broken, but it is different. If I zoom in, can you see the difference? This one has a split in it. Okay, so the one that didn't work is broken. That means that when I turned all of this stuff on, this didn't have a solid circuit. This couldn't carry a current. Because it couldn't carry a current, it couldn't feel the magnetic force. That's the difference. So if you have your solid loops, you induce the current going around the loop. If you don't have a connected circuit, you can't get that induced current. And if you don't have current, you can't feel the force. So anyway, that's a good place to quit. We won't have class on Monday, and watch Brightspace for details about the final exam. Yep.
Are we allowed to have a sheet like we have on the last semester?
I'll think about it and let you know on Brightspace.